The Mining and Smelting of Canadian Nickel, produced by Pathoscope of Canada Limited, sponsored by the Mond Nickel Company Limited. Nature's Storehouse and the Company Mines. The City of Greater Sudbury Archives invited 2 retired miners to discuss the mining procedures and other aspects of the life in a mine as shown in this silent film.
Hi, my name is Jim Dufour. I worked at Inco for 35 years, starting in 1965, worked until 1999, 20 years underground, the last 15 years in the training department.
Hello, my name is Jack Gingras. I've worked for Inco for 30 years. I started in 1968. I retired in 1998. The first 10 years I was a miner. And the last 20 years I worked in all mines training as a training instructor until I retired.
Diamond drilling to determine location and extent of ore body.
This would be a typical diamond drill setup. Here you see them drilling. Now he's removing the rod. Here you see them taking the core samples out. This is how they would determine if there would be any ore in this particular area.
A typical nickel mine. Let us go down to the mine and see how nickel ore is obtained.
Here you see the men loading into the skip as they prepare to go underground. The fellow would ring the bell. Here they arrive underground. The man takes the chain off and they unload, preparing to go into their work site. Here they're pushing their ore cars into the workplace.
We will follow the car through passages called drifts, far below the surface.
As you can see, it's awful dark underground. Here they change track to push their car into their work site. Here he would be loading his camp lamp up at the start of the shift so he could see what he was doing during the day. Lights were powered by carbide and water. Electricity was still not available underground in battery form. Here the carbide powder is loaded into the lamp, and the water and carbide powder create acetylene, which creates the flame. There is no danger using this method in hard rock mining. And now that he's ready, off he goes into his workplace.
The end of the drift. Drill runners preparing a blast to extend the drift to reach new work.
Here they're preparing to set up the drill. This would be called a bar and arm. Not a real safe operation. Here they put the drill on, which was quite heavy. Now he's putting the air hose on and installing the water hose. The air was used to operate the machine, the water was used to cool the rod. Here you would put the drill bit in, crank the machine and start drilling.
With compressed air force and great noise, the sharp edges cut into the ore while a stream of water pours through the hole to keep the drill cool.
Now that the round is finished, he would remove the air hose and water hose. Take the drill back off. And now they would tear down the assembly.
Fuses 8 feet long burn 4 minutes. Detonating cap being placed on end of fuse.
Here we would be putting a cap on the end of the fuse.
The cap is inserted in the charge of dynamite.
Installing the cap into the stick of powder. At that time, explosives were not kept underground, so they had to go to surface to get their powder. Here they would be coming back with their powder.
10 or 12 holes are made from 4 to 10 feet deep in a surface of 5 square yards.
The stick that he has in his hand would be for use for loading the powder.
1 stick of dynamite is placed in each hole for every foot of depth, about 30 pounds in all. The last stick in each hole has a fuse attached.
Here you see them tamping the last stick of powder in with the fuse. They tamp this all the way in. And they continue to do this with each hole. Here you see them attaching the wires together. The fuses would be let off with the cap lamp at that time. Here you see them lighting all of them.
We didn't wait to see what happened, but this was the result.
Here they come in with their car to start cleaning up the drift. As you can see, it was a back-breaking job because they would have to shovel all the ore into the car to clean up the drift. This would be done many times to clean out the drift.
When main development drift is finished, the ore above on each side is measured into sections called stopes, 100 feet wide, 100 feet high, and as deep as the ore runs, leaving a pillar of solid ore 40 feet thick between the stopes as a brace. Each stope is mined as a unit. Sub-drifts run from main development drift under each stope. Draw holes are run up at 45 degrees from the drift to develop the stope and draw out the ore. Each stope has several draw holes from 25 to 35 feet apart, a draw hole viewed from the drift.
Here you have a typical stope. Each stope is mined as a unit.
Let us follow the miner into the stope.
Subdrifts run from main development drift under each stope.
Here you see them climbing up into the stope. As you can see, it was a tight squeeze.
Here, a stopping gallery is made 8 feet high and full size of stope. The roof or hanging wall at the high side is cut horizontally and broken down, forming a perpendicular face, which is carried, blast after blast, the full length of the stope. These blasts are fired by electricity. Section after section layers 8 feet thick are blasted from the roof and broken up on the floor. Lumps too big to be broken up with hammers are broken with a small dynamite blast, blasting large lumps.
This is how they would have had to drill big chunks into the stope. As you can see, it was a dirty job. Here you would put in a little stick of powder, tamp it down with this, put another little stick of powder, put the fuse in, a little bit of dirt on top, tack it down, light it with his cam clamp, and run.
1/3 of ore is removed, 2/3 are left on floor to stand on in reaching the hanging wall when blasting down the next layer. This operation is repeated to within 10 feet of the floor of the next level above. When all the draw holes are closed, the miners enter and leave by raises from the drifts above. Miners going up out of a stope through a raise. These raises serve also as auxiliary shafts in case of fire or closing of mine shaft.
Here the miner is climbing up the manway to his work area.
When all the ore in the stope is blasted down and broken up, the draw holes underneath are opened and the ore removed.
Now they're going to remove 1/3 of the ore from the stope, and that so they can have enough room, enough headroom to take your next round. So they're filling up the ore car now to be transported to the skips. Now they're bringing in a fresh car to be loaded, and they'll repeat this process until the right amount of ore is removed.
As you can see, this was back-breaking work because everything done was by hand. Many times it would not run properly, so you would have to poke it down to get it to run. As you can see, it was not a real safe operation. Some of the chunks were fair size. Note, no glasses, no gloves.
This, the cheapest and safest method of copper-nickel mining, is followed in 90% of Mond Nickel Company operations. 100,000 tons of ore are stored in this way at one time. Diagram of overhead stope mining method.
This would be a typical ore setup. You can see solid ore, broken ore, mined out ore, the shaft going up, and the skip going up.
In the underhand method of mining, one draw hole is made at 45 degrees through the stope. Then a working gallery is made at the top of the stope. The ore is mined and blasted downward through the draw hole and removed at once. Seen in underhand stope.
This would be an undercut and fill stope. As you can see, the drilling would be totally different. They would have to drill down.
In an ever-widening series of ledges, like a great funnel, this ore is mined and removed. Men with scaling ladders constantly inspect the walls of partially emptied stopes to remove dangerous loose pieces of ore.
Here you can see the miner going up into the stope now. He's getting ready to scale the loose ground so it doesn't make sure it doesn't fall on him later. So that's what he's doing now. He's scaling the loose rock. He's sounding the rock to see the loose spots. The loose spots have a echo to it, and the solid rock you can feel it's solid. Now it's safe to go down.
The skip may be loaded direct from cars on main drift. Cars hold 2 tons, 2 cars fill the skip.
Here you can see where they're dumping the ore into the skips. They dump 2 cars per skip, then it's hoisted up the surface on in a skip box. This is the second car. After that, they'll hoist it up. He rings a bell, a signal, and on that signal, the hoistman knows when to hoist it up.
It is not always convenient to load skips at each level, or may be passed down through storage pockets to a suitable loading level far below.
This would have been an ore pass going from one level to another level where they didn't hoist the ore to surface.
The grading over the passage to lower level is called a grizzly and is for protection of men. This ore goes direct to loading pocket, a great bin cut 50 feet deep in the rock. From the main drift above loading level, ore is passed from cars through grizzly to loading bin.
Here they have the car dumped onto what they call a grizzly, and the miner breaks up the rock ore so it will go through the grizzly at a certain size so they don't get oversized chunks into the skips.
The ore is measured into skip loads weighing 4 tons. The skip weighs 3 tons.
Here you can see them emptying ore from one level, which would go down into what they call a holding pocket, to another level, because not every level had a train where they could pick up the ore.
This is the skip where they bring the broken ore to surface.
A waste dump on each level where rock is loaded direct into skip.
Another load of ore being dumped onto the grizzly. As you can see, the ore going down.
Drills dull very quickly and must be taken up to be sharpened.
Now they're going to surface with the drill bits, drill rods, and to be sharpened, and they have to lower them back on the ground later.
Ladders as well as the skip run to the lowest level. Telephones furnish communication between the drifts and the offices above.
Here you see them using the telephone to make a call to surface. More than likely ordering supplies.
The end of the shift, all aboard for daylight.
Here you see the fella ringing the cage. The men load onto the skip. End of the shift, and they're on the way up. Puts the chain back on. As you can see, he grabs a wire in his hand. That's the signal to the hoistman, letting them know that they're coming to surface. This would be the bell and the gauge in the hoist room. This is how the hoistman would know where he is. This would be the hoistman operating the hoist. Again, the level, so the hoistman knows exactly where the cage would be in the shaft. Here the men arrive on surface and unload.
Safety switch on operator's bridge stops all motion instantly in case of accident or danger.
This would be the hoist room. Again, the bells and the signal. And this would be the brake for the hoist. This is how the hoistman would stop it. There you see the thing shutting down.
Compensating balance of the two skips and cable.
This would be the skips going up and down. The one going up would be going to dump.
Skips carrying ore go direct to top of shaft house.
There you see another skip going up. Here you're going to see the skip dumping. There you are. The skip is emptied, and it'll go back underground to be refilled. Here comes another skip to be dumped. There you are, another load. It would then come down and go into the rock house at that time.
On next floor below, ore and rock is separated. Both pass through crushers and are broken up.
This would be coming now onto the belt. Here they would be sorting. This would be going through a little bit of a crusher to make it smaller.
From crushers, the waste rock goes direct to bins over railway cars. Ore goes through a revolving screen which sifts out the fines.
Here you see the smaller chunk coming out of the crusher.
On the picking belts, waste rock, low-grade ore, and high-grade ore are separated.
Here you have the belt where the men separate the ore and the rock.
Waste rock, fines, low-grade ore, and high-grade ore are being loaded into cars from bins.
This would probably be a load of waste coming out.
Let us inspect the equipment above ground before following the ore to the smelter. Power used throughout the mines, smelter, and town sites is hydroelectric generated at the company's own development plants and transmitted over 72 miles of line. Wabagizik, the company's first power development.
This would be Wabagishi on Highway 17, close to Nairn Center. See the car there?
"70 feet of head, developing 5,000 horsepower."
This would be one of the dams for power generating.
Two horizontal twin turbines develop 1,250 horsepower each.
These would be the power turbines.
This is what creating enough energy to power your mines?
Nairn Falls, 4 miles from Wabagizik, capable of developing 7,200 horsepower.
This would be now be Nairn Falls. This would be the outside of the building. This would be the dam.
Two single-runner vertical turbines develop 2,400 horsepower each.
This would be the power turbines. This would be the outside of the building with the train tracks.
The power lines, 44,000 volts, leaving powerhouse.
This would show you where the power was going to Levack in the north, to the smelter, Coniston, to Garrison, Worthington, and Victoria mines.
At mines, power is transformed to 500 and 110 volts for service, transformer station at mines. Three compressors supply 7,700 cubic feet of air per minute to pumps, air cranes, forges, skip brakes, and 70 miners' drills.
These would be the compressors.
You have 3 compressors to keep up a 90-pound pressure at all times.
As you can see, they were belt driven.
Sharpening ore drills, clearing water passage, and retempering.
What they're doing here, they're redoing their drill rods. They make sure that there's holes right through them so the water supply can go through, and they sharpen the bits with grinders to make sure the bits are nice and sharp for re-drilling again.
Here they would have different size bits depending on where you were drilling.
And he's measuring the bits now so you can put the larger bits first and the larger bits go last.
Here he's making a new drill bit.
The repair shops at the mine.
Each mine had their own repair shops.
The dynamite house is far removed from other buildings, only 24 hours supply kept on hand.
Because dynamite at that time was not really safe, it was kept far away from each site. This would have been a typical storage area for dynamite.
Dynamite freezes at 40 degrees and must be thawed out.
This would be a storage room at one of the sites for the dynamite.
The storehouse and mine offices. A shift is checking in.
This would be a shift just coming on.
A well-equipped emergency hospital for first aid.
This is your hospital in case you have an injured miner for minor dressings and in case they get injured.
The dry house. Hot air below, ventilation above, clothes are dry when needed again.
This would be the dry room. As you can see, he's lowering a bucket. This is where you would hang your clothes to dry during the shift. This has not changed. They still do this today, 100 years later.
And they hoist the baskets up to the ceiling, and then they blow hot air into the room, and the air goes through the clothes and dries them for the next shift.
This is where he would wash at the end of the shift. Today they have showers. They wouldn't use a pail and bucket.
Homeward bound, clean and happy.
Now they're on their way home after their shift.
At Levack Mine, connections with mainline CPR 4 miles distant is made over the Mond Nickel Company's own right-of-way and equipment.
This would be the train leaving the Levack area going to the Condison smelter.
Old Reliable, the Mond Mine at Victoria, 3,000 feet deep, the deepest mine in Canada.
This, what you're going to see now, is a head frame at Victoria Mine.
As you see in the background, the rock house where the ore is being dumped, then it's loaded onto those cars to be shipped to the smelter.
Worthington Mine.
This would be the head frame at Worthington.
Garson Mine has 10 levels and is the largest producer.
This is Garson Mine. Garson Mine at that time was one of the richest and largest producers and still is 100 years later today. The town site was built by Mond Nickel for the company, for the employees to live in. The town site still exists today.
Bruce Mine supplies 50 tons of quartz daily for smeltering purposes and pays its way by the copper produced.
This would be Bruce Mines, about 145 miles west of Sudbury. Mond used it for quartz.
The ore from all the mines is brought into Coniston, Ontario for smeltering.
This would now be the Coniston smelter.
And all the ore from the mines were transported to the smelter to be smelted.
All material is brought into smelter and moved from process to process in car load lots over standard gauge in railway or the company's own cars by the company's own motive power, or train arriving from the mines.
Here you have the ore cars being driven into the smelter from all other mines.
This would be a load of ore coming in.
All material entering smelter is weighed and taken to storage bins at smelter or to storage yard. High-grade ore on the scales.
As you can see, there wasn't a lot of safety.
And every car is weighed, so they'll know how many tons. And there's a weigh scale there. And that way they know they can record all the tonnage that goes into the smelter.
This would be the tag that he would have after he weighed the car.
Unloading high-grade green ore at the storage yard.
Often they would have more ore than they could smelt, so they would dump it in the yard. Here they would stockpile it.
The storage yard. From the scales, the green ore may be taken direct to smelter storage bins.
Here they're dumping a load of ore onto one of the grizzlies.
Ore having as low as 15 to 20 pounds of copper nickel to the ton and formerly rejected is now separated by a system of oil flotation. Low-grade ore is first taken to the rock house and broken up.
Another load coming in. Lots of this had to be unloaded by hand.
There's the ore coming out of the rock house.
The flotation mill, where low-grade ore passes through a series of processes to secure the small amount of valuable metal. Here the ore is ground as fine as meal between rolls and screened.
This would be a crusher. Here they're grinding it up into fines. As you can see, the fines coming out.
The oversize returns to the mill. The fine is mixed with water in a feeder.
Here you see the fines being mixed with water.
The concentrating tables make the first separation of metal from dross. The concentration of valuable ore pass over end. The dross is washed over the side.
This would be on a belt, like a shaker, and it shakes the excess off the side.
The concentrates pass to the settling tanks. The rejected ore is carried into a tube mill and ground very fine.
This would be a grinder where they grinded it up. Here it comes out at the end.
Very fine ore is carried to first flotation unit, oil and sulfuric acid are added, and the mixture is churned into a froth.
As you can see, everything was belt driven in those days.
The valuable ore is coated by the oil and floats to the surface in the bubbles.
Here the ore would be in the bubble form.
The remaining ore settles at the bottom and is drawn into second unit, where it is again churned up and concentrates removed. This process is followed through 10 similar units. Finally, the middlings are returned to the head of the system, tailings going to dump.
Here he's checking to make sure everything's come out correctly.
And they're separating the waste with the good minerals.
Concentrates are sent to settling tank, where ore gravitates to bottom, water overflows into receiving trough.
This would be a settling tank.
These concentrates, also fine green ore from mines and valuable flue dust from the blast furnaces, are fused together in sintering plant. Cars of concentrates, fine ore, and flue dust are emptied into bins at top of sintering plant.
Another train going into the rock house, dumping another load.
Gates measure correct quantities onto endless belt carriers.
Here you see it coming off one belt, going on to another belt. travel up to different locations and be separated.
Separate it into two streams, one for each sintering machine.
Here it would be coming off the belt, catching on to a board, being scraped off the board, and dumped. This would be a grater. Any large chunks would fall under the grater and fall off.
Loading the sintering machine, coarse grain on bottom, fine on top.
Here it would be getting ready to go into the furnace. This would be the fines now getting ready for the furnace.
An oil blast is forced through the sinter to firebox below, causing incipient fusion of all particles together and removing 15% of the sulfur.
This would be coming out at the end of the furnace. Here you see the fella breaking up the ore with a hammer. Here you see it coming out and being dumped off the end on rollers. This would go into cars. Here's the cars here.
The fusion or sponge-like formation binds the particles together, yet allows free action of furnace blast, increasing the furnace capacity for green ore.
This is what it looked like after coming out of the furnace. It would look like a chunk of coke. See the holes in it?
The sinter is taken to smelter storage bins. Loading high-grade green ore, sinter, coke, and limestone onto furnace charging cars at bottom of storage bins.
Here they would be loading it into a Hudson car. You can see it was being moved by a small electric trolley. 10 to 15 cars at a time.
Charging one of the 4 great furnaces, each with capacity of 750 tons daily, 4.5% metal value. This process is constant.
Here he would be weighing each car. Here he's opening the door to the furnace.
Then the Hudsons are dumped, the ore is dumped into the furnace, into a bin to be fed into the furnace.
As you can see, each car needs to be dumped 2 or 3 times to get all the ore out. Now he closes the door to the furnace and opens the other one so you can see inside the furnace. There's the furnace.
Lower section of blast furnaces and water jackets. Air pressure pipes, exhaust stack, and passageway from storage bins to smelter. 22 tons of valuable ore dust is collected in these flue bins daily. Flowing at a temperature of 900 to 1050 degrees, molten metal is constantly pouring into the settler. The settler, the limestone added in the furnace charge, has heated the iron and rock, making it fluid. Being lighter, this dross rises to the surface in the settler and constantly pours off in the form of slag.
Here you see them filling up a slag pot.
And the slag is the waste product from the ore, and it's to be dumped in a slag dump later on.
Slag pots, each holding 40 tons, being emptied on the slag dump.
They're on their way to the slag dump now with the slag.
Here they're dumping the slag by hand. Today they don't do it by hand. Here you see the slag coming out and going down the hill.
And when the slag is dumped, it's still molten, red hot. So at nighttime, people come and visit that.
Pouring 100 tons of slag at night.
This is what it'll look like at nighttime.
And the slag would be very hot, red hot, until it cools. Then it dries up and it becomes like a solid rock after that.
Over 1,000 tons of slag are added to the stump every day.
Here you're going to see them repairing some track.
Let us return to the settler. The ore enters the settler 4.5% nickel copper from the furnaces. The iron rock flow the top as slag. The nickel, copper, and some iron gravitate to the bottom and are drawn off at intervals in great ladles. The furnace mat is 16% nickel copper.
He's punching the furnace so the molten will come out the bottom. Here they're pouring it into a pot to be transported.
Lifting 15 tons of molten metal from settler to the magnesite brick-lined converters.
This is a slag of ore going down. This would have been called a converter aisle.
To this molten mass is added silica quartz from Bruce Mine as a flux. Adding oxygen under 12 pounds pressure, the iron is mesmerized at a temperature of 900 to 1,100 degrees. The iron slag is drawn off at intervals and returned to settler, where any remaining nickel copper gravitates to bottom. As ore and quartz are added and slag drawn off, nickel copper deposit gradually rises in converter to 45 or 50 ton weight when 80% copper nickel, called 80% Bessemer matte, is drawn off and poured into molds.
Here they're going to dump the ore into a mold. This was done right on the floor. There it goes into one of the molds.
Cooling, breaking, crushing matte.
It is then cooled. You can see that water cooling it down. Now they're breaking it up by hand. Hard work. Pick up the chunks, throw them on the floor out of the mold, break them up even further. Pick them up, and they throw them into a little crusher. Here you see the little crusher, and they're crushed up into real fine.
Measuring, weighing, barreling matte for shipment.
From here, they're loaded into a barrel. Take a hammer, pack it in, put the wooden top on, and the last ring goes on. Now they nail it so it doesn't open. And then they dump it, and each barrel is weighed. Here you see them lifting up and weighing it. And then he'll mark it. Now they're ready for shipping.
Or en route to seaboard.
This would be a load of finished product being shipped overseas.
The smelter equipment, the powerhouse, company's own hydroelectric throughout. 6 company locomotives are housed here.
This would be their locomotives. This is where they would have stored them. They had 6 of their own locomotives at that time.
General view of company's well-equipped repair shops.
This would have been their repair shop. They would have done all kinds of repairs here, from woodworking to sheet metal to anything else that company needed.
And each mine site had a complete workshop.
Here you see the fella doing some cutting of steel. Here they're doing some planing. Here they're doing motor repair, probably electric motors. This would have been the blacksmith shop. Riveting. Notice the pipe. Here they're doing repairs to one of the slag cars.
The storehouse, where $250,000 worth of stock is kept. The laboratory is finally equipped with metallurgic work.
This is where the fellow was checking the fines, the final product, to see what would be coming out. You see him putting him back in the machine. He'll clean that out once more. Do another final check. And check again to see if the quality is good. This would have been the lab.
The drafting room.
Here's where they would have done a lot of drafting for the underground. They would have prepared and said, okay, this is where you drill and blast.
The general offices.
This would be the general office at Coniston. This would be at the end of the shift as we see they are leaving.
All aboard for town.
Here you see them boarding the train. This was the means of transportation as there were no roads at this time. This is how they would get back and forth to their work sites.
Coniston from the hilltop. 1,200 population, half mile from smelter.
This is the town site of Coniston. Note all the outhouses. Most of the homes were 1 story. A couple of them were 2-story. Note the church in the background. You can see the chimneys in all of them, so they were probably all wood-fired at that time. Coniston still had some trees there.
Bessemer matte, 80% copper nickel.
This mass was the finished product at the end of the process. And this is the end of the video.